this for flat PCA or just like in general?
Yes, so we have 3 or 4 memory scores for the project.
Oh, that's right.
Yeah.
You mentioned that.
It's figuring out which one of those
Yes.
to use or compatible.
Yeah.
So in your data set, how many, so you have 3 variables and you have like many subjects or?
40.
Oh, okay. Okay, that's good. That's a nice example based on what I've prepped. Okay, so I know. It was the kind of thing when I started, I wasn't really planning on doing it this way, and then it just kind of, yeah, grew. So we're going to talk about principal component analysis. This is going to be very focused on like the practical side of it. I do go through the concepts of how it's done, but I don't go deep into the math side of things because honestly it's just beyond my capability. So, but I've included some resources at the end if anyone's super interested. Okay, so why do we use PCA? So generally it's to reduce a high dimensional data set into fewer dimensions. And when we say dimensions, we basically just mean variables. So in your case, Hilary, if you have 3 variables, is there a way that we can combine those together to maybe just have 1 or 2 variables? So often variables in a data set are correlated, and it's possible to combine these correlated variables into new, that is fewer variables, also known as principal components. And then when you have fewer variables, it can be then easier to identify trends or patterns in the data set, and it can also reduce the number of statistical tests that you have to run as well as correct for. If, however, your variables are completely independent, so that means that there's no correlation between them, PCA is not useful. So it's kind of a good first step to explore some correlations between the variables, just to make sure that it's worth going down this path before you do it. But with a lot of the kinds of things that we study, especially because we're looking at things that occur, biologically or cognitively or whatever, the chances is that they are going to be correlated. So how this basically works is that you can plot your data or have your data in all of the dimensions, and you look for the direction, so that is the linear combination of original variables in which the values are the most spread out, and that is your first principal component. Then to get your next component or your next principal component, you look for the next direction with values most spread out, but they are also uncorrelated with the first principal component, and that's the second one. And then you end up with the same number of principal components as your number of variables. So you keep finding the next variable that's most, or the next direction that's most spread out until you have the same number of principal components as variables. And then once you have all of that done, you're going to look to see how many of these principal components you actually need in order to capture most of the variation in the data, and then you'll just use these like subset of principal components in your subsequent analyses. So does that all kind of make sense so far? Yeah, give or take. We're going to walk through an example with more visualization because it can be hard to picture, but this is kind of like the bones of what we're going through today. So this is potentially what your data set looks like, where you have 1 to n number of variables and you have 1 to n number of observations. In PCA, there's no assumption about the structure of the data, so you can have, you might just have 1 observation for each subject, or you could have multiple observations per subject, per condition, per run. They can be like related. I'm not sure if I'm saying that very well, but basically there isn't an assumption of independence between your observations. So it's not like if you're doing something like multi-level modeling where you have to specify the structure of the data so that can be taken into account. With PCA, everything can be related in many different ways, and that's fine. Okay, so let's walk through an example of 2 variables. This isn't very it's not a very good realistic example of PCA, because if you only had 2 variables, you wouldn't need to do PCA. But it's much easier to visualize things in 2D than in, let's say, with 20 variables. So this will get you used to the terminology that's used, and then we really just scale this process up if you have more variables than So we have variable 1 and variable 2 and some data points plotted in 2D space. And the first thing we do is estimate the mean for one variable, then we get the mean of the second variable, and then we find the center of the data, which is just where those means overlap. We then need to center that data. So what we do is just we take the center of the data and we move it to the origin. So now if we just go from here to here, we've just like all the data are still in the same orientation, but they've now just been centered so that the center of the data is at 0, 0. And then from here, we fit a line of best fit. So this is very, very similar to what you do in a regression. You find the line where you're minimizing the error in the data. And this actually is your first principal component. It's often described as a linear combination of your two variables, which for a long time I didn't really understand what that meant. But basically it's just saying that this line here, so the first principal component, is a combination of this variable and this variable, and in this case it kind of looks like it's more influenced by variable 1 than variable 2 in terms of how it's sloped. Then from here there are a few more bits of information that we can pull out. So one thing we can look at is the spread, and just how I said here, variable 1, there's greater spread in that variable than in variable 2. And then we can also estimate the unit change based on these variables. So in this example, for every 3 unit change in variable 1, we see a 1 unit change in variable 2. And because these make a triangle with the first principal component, we can then also estimate the length of the principal component at the same point. And in this example, it will give us a value of 3.16. In PCA analyses, though, we like to, I guess, always use like a standard unit of measurement. So to do that, we actually calculate, instead of leaving this at 3.16, we scale it down so that we're looking at what a 1 unit vector on the line of the principal component, how that relates to these other 2 sides of the triangle. So if we basically just divide all of these numbers by 3.16, and we end up with these values. And then what we can say is that for every 1 unit change in the principal component, it consists of like a loading of 0.95 on variable 1 and a loading of 0.32 on variable 2. And so all of these things have terms. So this 1 unit vector is sometimes called the singular vector and sometimes called an eigenvector. And the algorithm that is used in MATLAB is called the singular value decomposition algorithm. And this is kind of where that comes from. And the process that I'm describing is most closely aligned with that algorithm as well. And then these scores here that describe like the loading or the weight of the variables, these are called loading scores. Okay, so then quite simply, actually, the principal component 2, or the second principal component, is then fit in basically the opposite or perpendicular direction to principal component 1. So as we said in the earlier slides, this is the second direction that has like the next most spread in the data, and it's also uncorrelated with the first principal component. And just as we did for the first principal component, I'm not going to go through it here, but you can, estimate, your eigenvector and your loading scores for each subsequent principal component. And then after you get your principal components, the last thing you do is you take your original data and you re-express it in principal component space. So what we've done here is we've just taken data that was, kind of on its side. We've rotated those principal 1 and 2 components around so that now they're horizontal and vertical, and that data has moved with them. And if you were then to decide to use, let's say the first principal component in your analysis, because that's counting for most of the variance in the data. It's these re-expressed scores that you would be using in the analysis. Okay, so then there's just one more kind of set of terminology that I'm going to go through before we get to the MATLAB example. So when you have your data points plotted, this is in the original space, not in the principal component space, you can estimate something that's called an eigenvalue. So this is the sum of squared distances between all of these points and like the zero value of that variable. And this, it's like an estimate of variance, and that we're going to use in another calculation in just a second. And then you would estimate an eigenvalue for both or all of the principal components that you have. And how we're going to use this is to come up with a calculation of proportion of variance explained. So for each of these eigenvalues, you're going to divide it by the total number of observations minus 1. And then you'll sum these together to get the total variance. And then to get the proportion of variance explained per component, you'll just take, the first part of this equation and divide it by the total variation. And so often how this will then come out is that, let's say your first principal component might explain 80% of the data, and your second principal component might explain 20% of the data.
The eigenvalue is the lines that are drawn there.
So
that distance.
Right. So the eigenvalue
is
is
to go to the 0 point of variable 1.
Yeah. Of the origin. Yeah.
Okay.
And then for right, and then you would do the same for like your second, your second principal component would be this way, and then you would do the lines in the other direction. And so what we're really getting at here is, how, if we go back to here where we see the 2, so how long is, this line, like what is the spread of that data versus the spread of this data? And that's, it's an important metric that we'll see later on in terms of how you decide how many components to include. Okay, so does that kind of make sense so far?
Yep.
Okay, so then let's go to MATLAB. So in MATLAB, the basic function is just PCA X, where X is a data frame. So Hillary, in your case, what you'd have is 40 rows by 3 columns. Right? So your observations in rows and then your variables in columns. And if we were just, just to ask for just the coefficient outputs, if you look at the MATLAB documentation, it tells you that this returns the principal component coefficients. And here I've included an extra column for translation because sometimes the terminology that's used in the MATLAB documentation is different to what is used typically in statistical lingo. So in all of my explanations so far, I've kind of stuck with more of the terminology that you'll read if you read papers or other tutorials, but then they don't match up quite as nicely with MATLAB. So and this is something that when I first started working in PCA, like that was a stumbling block, like an unnecessary stumbling block. So trying to, right. So the principal component coefficients are what I've called loading scores in the previous slide. So if we quickly jump back, it's saying that, this principal component is loaded by this much variable 1 and this much variable 2. So there are coefficients. Another way you can run PCA in MATLAB is also by asking for output related to score and related to latent. So here, score is the data in X, so your original data that is now re-expressed in principal component space. And so as I said, this is the data that you would use in subsequent analyses if you want to just run, let's say, you want to look at the first principal component and compare that between your 2 groups, then that is the data that you would use in that analysis. And then latent is it's like the variance, or what we've previously called the eigenvalue. So I don't often use like the raw latent score, but it's there if you have some use for it. The next thing you can ask MATLAB to output is t-squared. So that's a Hotelling's t-squared statistic for each observation of x. To be honest, I've never actually used this, but my understanding is that you can use it in some kind of model diagnostics if you were to use these principal components to predict some other data, you know, and then basically it's an option. I don't think we'll need it for our purposes, but you can read more about it if you want. There's a couple more options you can get. Explained is the percentage of the total variance explained by each component. So just as we showed here, it outputs that for you, so you don't actually have to do this calculation, which is nice. And then the final thing is the mu value, which is the estimated mean of each variable. So typically what I would use is this combination. So I ask for the coefficient so that I can understand the different loadings on the different components. I output the scores because I'll probably be using that in follow-up statistical analyses. I then use this tilde sign, which just suppresses output that you don't want in MATLAB. So the order of these has to be maintained. Like you can't just pick and choose which ones. So I'm basically using this second last row version, and then I'm using tilde to suppress latent and to suppress t-squared because I'm not going to use them, and then I'll also output the explained variance. Okay, so now to an example. So this is data that I was working with from the S-rate study, and I had 2,240 observations, and I had this many observations because I had 14 trials by, 14 subjects by 4 runs by 40 speaking or sentences. So altogether, it adds up to many observations. And then for each observation, I had 3 variables, and these was F0 contrast, intensity contrast, and duration contrast. And so the idea was, can we reduce these variables down to 1 or 2 components that I could then use in further analyses. So I'm just going to call the data matrix data. And then I'm going to run, as I said, this is kind of the function that I would typically use. So asking for a coefficient, score, and explain variance while running the PCA over my data matrix. So the first output we get is coefficient. And as I said, these are the loading scores. For each row contains the coefficients for the variables, and then each column corresponds to the principal components. So if we were just to look at the first principal component, this is basically saying that we see the greatest loading on, let me see. So I always find it hard to tease apart which is which. Okay, so my variables are ordered FO, intensity, duration. And so the first principal component has the greatest loading on duration, followed by intensity, followed by FO.
So the columns are the coefficient, are the components.
Yeah. Whereas the second component has the greatest loading for intensity, followed by FO, and then a very small contribution of duration. And so on. And I'm going to come to a way that you can plot this that makes it easier. But it's just good to know how to interpret the raw output.
Repeat what the variables were again?
Yeah, oh yeah, sorry. So it's FO, contrast of FO, contrast of intensity, and contrast of duration.
So the image contrast.
No, sorry, these are the acoustic measures.
Acoustic measures.
So where we did,
okay, gotcha.
Yeah. So then the next output we get is the score. And so here you'll actually get one row for each observation. So I would have had over, 2,200 rows, but I didn't include them all here for, sake of space. But here, so each row contains data from one observation re-expressed into the principal component space. And just as for the coefficient, the columns correspond to the principal components. So the first column of score is all of that data for the first principal component now re-expressed in that space. And so if you wanted to pull out that data for further use, you would just use this syntax here where it's score, all rows, first column. The next output I get is explained. And so you get one value per component. And what this means is that the first principal component here accounts for 96% of the variance in the data. The second principal component is close to 3%, and then the third principal component is about 1%. So really what this is saying is that, just by using the first principal component, we're pretty much capturing all of the variation in the data. So it's unlikely that we would need to include any more than one component. So going back to the coefficients, which are the loading scores, there's a nice way of plotting these, but we can really only plot the first two components. So if you need to plot, you can obviously plot in higher dimensional space, but plotting in 2D is much more intuitive. So if you have an example where maybe you do actually have 3 or 4 or 5 components that explain the data, this plot might not work. But if you have an example where just 1 or 2 components explain the data, this plot will be very helpful. So the plot is called a biplot, and you're basically plotting the loadings and the scores, and then we're going to label the variables so that we don't have to remember exactly which is which. And this is what it ends up looking like. So here we have our first component, and here's the second component. And what this is telling us is that the first principal component is loaded or weighted by the val duration contrast, whereas the second principal component is loaded primarily by the intensity contrast and also a bit by the FO contrast. So it really takes all those loading scores and makes it very intuitive as to what it means.
When you just do a correlation between the 3 variables, pairwise, are they correlated?
It's a good question. So, right. So I went back, and when I first did this, I didn't actually look at the correlations, which I now realize was a mistake. So val duration, intensity and FO are very strongly correlated, and val duration and FO are a little bit correlated, but the other 2 are not. But I think here what we're seeing is that maybe this is not the best data set to do PCA on, because duration, it's not as correlated as you would expect for a PCA.
When you go back to the coefficients, those loadings, it's like there's each one is really loading onto a component, and there's not much loading from the other ones.
Right. I think like PC2 is a better representation of what you could end up with, but the fact that the first component is so heavily weighted by val duration is kind of suggesting that val duration is out on its own.
Right, and that seems like that's what you need to be careful here. Is
right.
If you just pick one and you say, okay, this this is a representation of these 3 variables. In this case, may not be actually. They're actually maybe 2 different things going on, and you might see something interesting if you looked at val duration on its own, and then those other 2 combination orders separately. Where with yours, they're really they're very highly correlated. So that's the one where it seems like the two digit spans may be doing something different than the repetition task, but that's what we can kind of tease out by using that with this.
They're all correlated, but not
Yeah,
Yeah,
that's
kind
like
of
a mess.
evenly so, yeah,
Mhm.
grasp that.
Right, and so that would be a better example or a better use of PCA. And yeah, the nice thing about going through this is that that kind of highlighted that for me, was that maybe this wasn't the best thing to do for this data.
Would it be legit to say that by doing this though and using the first component? No, it would not be. I was going to say, are you removing some of the effects of these other things? Like you're removing the covariance of those two things on
Yeah.
validation, but you're actually still, it's not exactly that, because you're
Right.
not looking, you're almost looking directly at validation, but you're not quite
Yeah,
looking exactly.
little vehicles, yeah.
Yeah.
So it's a necessary prerequisite that all of the variables be correlated.
Mhm.
Needs to be
At least
appropriate.
somewhat. They don't have to be highly correlated, but they need to be somewhat correlated, I think.
I think this is still legit to do, right?
Mhm.
I mean,
Mhm.
this is, I'm really speaking, this is speculation.
Mhm.
So you can follow this up with someone that knows what they're talking about. But just from a intuitive level, I would say that it's still legit to do this. But if they're not correlated and you do this and you just go with the highest component, which will be the one that varies, that just happens to be the one that varies the most, that you might be throwing something away by not looking at those other components, because the first component here is all valid duration. And the fact that they're not correlated means that there could be something else interesting that you could get by looking at the other two, either separately or in combination.
Mhm.
Maybe, and you would determine that potentially by using PCA. But you could be tossing something out. Like there's some variation that's totally uncorrelated with valid duration that you might be able to capture in whatever you're going to be looking at.
And if these components like had a contribution from all of the variables, like those blue lines would not have aligned quite as well with the axes. Like you'd see them kind of in space,
Okay, yeah.
and then that would, the closer it is to one,
Intensity
right?
starting to-
Right.
Yeah, exactly. Yeah. And here, like validation is pretty much like on the line, so it's like that's pretty much all validation. Another plot that we can use to help determine how many components to use is called a scree plot. And in MATLAB, I'm not really sure of the connection here, but this is the syntax. You write Pareto and then explained. I'm sure there's a connection with that word. I've just never heard of it before. But what this will plot is all of the proportion of variance, and you'll see typically what you'll see is a bar for each component up until you reach 95% of the proportion of variance explained. In this example, because the first component had over 96% of the variance explained, we're only seeing it for the first component. But I've included a couple more examples because this is a little there's really nothing to interpret because we're only seeing one. But if you had many more components, this is the kind of thing that you would see. So in this example, the first component is explaining about 73%, 22%, 3.7%, and so on. And so this is called a scree plot because the idea is that the first part of the plot looks like a mountain, and then as it levels off, this is like the mountain scree at the end. And here, what you're looking for is what they call an elbow in the plot. So here, I would say the elbow is here. That's where it really, like the line turns, and then you go back one. So in this example, two components would be good enough to describe the data. This one, it's not quite as clear, but maybe, I don't know, let's say the elbow might be around the sixth component, so maybe 4 or 5 components would probably do a good job of explaining the data here. So it's not a hard and fast rule, but it does give you an idea of how much variance you're explaining. And really, once you're getting up to about the 90% mark, then that's going to be a lot of variance explaining the data. And that's pretty much it. I included some extra information about there are these name value pairs that you can use as alternative input arguments in MATLAB. So it would be something like this, where you're running PCA on this X data frame, and you can change things like the algorithm, whether or not the data is centered, how to deal with missing data, etc. I went through these, and for the most part, like, I have included this information, but I'm not going to go through it now because it's a bit tedious. But for the most part, I kind of determined that generally the default settings are fine. And except for this one, if you have missing data, you might want to switch to this ALS algorithm. But otherwise, I would just stick with the defaults. And then I just included some extra resources if you want to know more. And that's it.
Wow. Very good use of time.
Thank you.
Tutorial.
What, this is probably like a very basic question, but like